Hello, my name is Giacomo. Thank you very much for having me here. I work at RMIT University. My supervisor is Nick Manicucci. We also recently got this website up and running, and our group is named Kermit. Now, as you probably all know, there's two macro settings for quantum mechanics that can be approximately divided in discrete variable quantum mechanics and continuous variable quantum mechanics. The reason we like discrete variable quantum mechanics is that there is a very practical and nice notion of quantum computing defined over it. What I specifically care about is encoded CV quantum computing. So the idea is very simple. We just take two wave functions and we map them to two qubits, R0 and R1. Now, these wave functions are obviously the Hilbert space of CV quantum computing is very large, and we have a lot of freedom in the choice of these wave functions. So we're going to have to make choices to maximize stuff like resilience to errors, ease of implementation, ease of practical implementation, and once we have picked our wave functions, our codes, we can benchmark our codes. We can, for example, categorize them with respect to their symmetry properties. We can define a notion of fault tolerance. We can concatenate them with qubit codes. What I'm going to be talking about is one very specific code, the Gottesman-Kitaev-Preskill Code. That was a code initially introduced to protect against small shift errors, but it turns out that it doesn't just protect about that. So let me show you how it works. This is the wave function for our 0 state. This is the wave function for our 1 state. And if we want to encode a qubit, we do so by changing the relative amplitude of these two infinite Dirac combs. Now, suppose we want to perform qubit readout off of this wave function. We just perform a homodime measurement, and we have a look at where our quadrature ends up being measured. As long as we're inside these bins, these root pi size bins, we still associate our results with a particular qubit. So that's why it's resilient to small shift errors, because it doesn't matter whether our wave function has shifted a bit. As long as it's in the right bin, we can say, okay, that was a 0 or that was a 1. Now, how is error correction performed? Clearly, we need to not collapse the logical information. So error correction essentially works by measuring only by how much our wave function has shifted with respect to the original grid. So GKP error correction is pretty much just we can see it as a gadget that acts on as a CV quantum circuit that acts by telling us this the value of this quadrature mod root pi operator, so that we can shift the state back. We can snap it back to grid without knowing what the logical information actually was. Now, that was a highly unphysical wave function, and GKP Gottesman, they addressed this problem by giving a physical version of these wave functions. So we have our comb that's multiplied by an overall Gaussian envelope, and that's also blurred, Gaussianly blurred. Now, there's two problems with this. The first problem is that, as we can see here, our 0 is like leaking into a 1 state. That means that our base wave functions, that our wave functions for our qubits are not orthogonal anymore. And this overall damping by a Gaussian kills the periodicity of our states, meaning that shifts by a full period no longer stabilize code words. This means that we're losing some of the logical properties of the GKP code. Now, before I address this issue any further, let me point out that there has been that ways to deal with periodic or quasi-periodic systems in quantum mechanics that have been around for quite a while, especially these two papers. One came out in '68 and the other one came out in '69. Essentially, they cook up a toolbox for dealing with this type of system. Much more recently, this other paper came out. It's a very nice paper where they point out that these methods could actually be applied to quantum information theory, to CV quantum information theory, because the GKP code is a periodic wave function, and they define some approximate logical operators and so on. Now, what's the idea behind these tools? The idea is very simple. We just start from the fact that a real number can be written as just a quotient functions plus a remainder function. We decompose our quadrature operator as this integer times root pi. Root pi is chosen because of the fundamental GKP spacing. And we operatorize, if you will, this relationship for the real numbers, and we end up with two operators, one with the bounded spectrum but real, and another one with an integer spectrum. In this paper that's out since last week, we discussed a technique to define a qubit out of this realization, out of the fact that we can get these integer operators. And as you probably could have guessed from how the GKP code works, by labeling qubits by the parity of the bins, that's exactly what we do. We take this integer operator, m here, I'm just representing the number, and we say that we have a subsystem of the whole oscillator, harmonic oscillator Hilbert space, and we label this with the even-odd parity of this m operator. At this stage, we haven't defined any code. We're just saying this is how we're gonna be writing a basis for a Hilbert space. So we start from this mu basis, which would be the bounded and integer, the basis for the full mode space labeled by the an integer and a bounded numbers, and we decompose it this way. And we can actually start, and this actually defines a very well-defined and nice notion of a qubit. Let me first show you a very ad hoc example, though. So we take a periodic wave function, physical. We split it up in a bunch of bins. We label them 1, 2, 3, 4, 5. We separate the evens from the odds, and we label the pairs. Now we use the qubit to label which subsystem we are in. So we end up with this, with what we have on the bottom right. Now, why do I say that this example is ad hoc? If you look at these wave functions, the one on the top is simply just a phase, just a minus the wave function on the bottom. Therefore, we have a product state, and what we end up with is this fully separate, separable state. In this case, we have encoded a minus because the phase was a minus. More examples. Let's take a GKP plus, a perfect comb, a perfect Dirac comb spaced by root pi. That's a separable state. It's a plus logical C2 that lives in a C2 subsystem, and the wave and the gauge, what we call the gauge mode, the gauge wave function is the leftover wave function, which is infinite dimensional. It's exactly the same as what we started with, the wave function for a GKP plus. The GKP plus encodes a logical plus. Well, that seems to work. Let's take zero momentum eigenstate. They're just flat wave functions. What do we have? We have a logical plus and the wave function for a 0p itself. So both these states are self-similar in this respect. What we can see here is that we take two very different wave functions, but they encode the same logical state. And the reason for this is that they're both periodic with the right period. Now, in real life, in general, states will not be separable. Logical and gauge subsystem are entangled. This entanglement means that there's going to be decoherence of our logical qubit that's given by the gauge mode. And how do we retrieve that information? Well, in a Hilbert space, there is a very natural map, the trace, so that once we trace out the gauge mode, which is by our own definition, whatever we don't care about, whatever does not carry logical information, what we're left with is just a density matrix. Now, what happens is that whenever we have a separable state, this density matrix represents a pure state, pure qubit. When our states are entangled, when our gauge mode and our logical subsystem are entangled, which would be the case of, for example, an approximate GKP state, we have a mixed qubit. So once we have this map, we can just pick any CV state we want, any wave function, and trace the gauge subsystem out and just look at the qubit. So this, as we can see, is just an example of a GKP plus state approximate with a fixed envelope parameter. With a fixed spike parameter and a varying envelope parameter. So once we have parameterized this state, we just trace the gauge subsystem out, and we follow the block vector. So we can see that, for example, what we want is a perfect logical plus with high purity. So we start with an excellent state, and that's pretty much a pure qubit. The block vector is about 1. Then the state starts having the block vector becomes less than 1, and then we can keep following our qubit. We see, for example, in the bad case, we're kind of halfway there, and when we keep changing the envelope parameter, we'd end up with a high purity logical 0, which is not what we wanted to represent. What we wanted in this case was a plus. We can do this to gates. We can do that to channels. This is just an example. Another very nice thing that this subsystem decomposition does for us is it gave us more insight on continuous variable cluster states, which is something we work on a lot. So DV cluster, discrete variable cluster state, is known to be a resource for fault-tolerant quantum computation. We have a CV version of that, but that CV version deals with just Gaussian states. So once we use encoded codewords on top of CV cluster states, then we can define a notion of fault tolerance, and therefore we have something we can use to do discrete variable algorithms, say. So let me fix some notation. On the left, we have a logical discrete variable cluster states that we use diamonds. So this is the easiest possible we can think of would be the plus plus connected by a CZ operator. And on the right, we have the CV counterpart, two zero momentum eigenstates connected by the CV version of the CV operator. It turns out that we can extend the CV cluster state formalism to the subsystem decomposition. And we can see, we do that by giving a decomposition of logical mode, gauge mode, and the operators themselves. These operators are the lines, and they represent generalized CZ operators that entangle the various subsystems. So what happens here is that when we take an ideal continuous variable cluster state, we recover a discrete variable cluster state on the top, the two diamonds, but this is badly entangled with the rest of the system, which is bad in theory. Now, how do we retrieve the logical information? Well, the key is into the code itself. We need to pick a code. And it turns out that modular position measurements, that is attaching a GKP ancilla, so an encoded ancilla, and measuring, it can be reinterpreted in this formalism as just a disentangling operation. So if we take this cluster state on the left, which is entangled with the gauge mode, the discrete subsystem is entangled with the gauge subsystem, but we use two GKP encoded states, two GKP encoded nodes. That's, with respect to this formalism, this means that we have a perfect discrete variable cluster state and complete disentanglement from the gauge subsystem. So the gauge subsystem does not mess up our state. This is the ideal version. What we really care about is seeing what happens with physical systems, with physical channels, physical things in general. So what we did, once again, this is an example that we picked. This example would be encoding a node with the GKP code, and then teleporting this node by just measurement, by on measurements. We teleport this encoded state out on a chain of CV nodes. Now, for the ideal case, we will have just perfect teleportation and our state does not decohere. It's just nothing really happens. If each node is a finitely squeezed state, each teleportation corresponds to some loss of fidelity with respect to the logical qubit. Once again, since we have this mechanism of just tracing out the gauge mode, and we have this intrinsic notion of qubit fidelity with respect to the qubit that we're trying to encode, we can simply just plot the fidelity in this case. The example on the left is 13 dB of squeezing, for example, and we see that the plus state gets a 95% fidelity with respect to the perfect logical plus after 3 teleportations. On the right, we have a more robust example, 16 dB of squeezing. We see that the state survives for a bit more. These are just illustration on. This is just to show that it behaves as one would expect. Yeah. Note that different states perform differently. Now, since I have time, I'm going to be talking about this other result that we did a couple of months ago, and this is definitely we switched gears, and I'd like to start with an analogy, with another analogy between qubit quantum computing and continuous variable quantum computing. We have the Gottesman-Kitaev theorem. It's telling us that if we start with Pauli eigenstates, Pauli to Pauli gates, and computational basis measurements, if we add just a single non-Clifford element on top of this, then we have universal quantum computing. This just translates to continuous variable quantum computing by replacing Pauli eigenstates with Gaussian states, Clifford group with Gaussian to Gaussian states, gates, computational basis measurements with homodyne measurements, and the non-Clifford element in this case would be one non-Gaussian element. Here I'm saying element because it could be a state or a gate. It doesn't matter. What we did is the idea initially was that to do that, to get to fault tolerance with with continuous variable quantum computing, there was, if we read the GKP paper, for example, there were two non-Gaussian resources involved with fault tolerance. One was the GKP state itself, which is non-Gaussian, and it's used to encode. And whereas the other resource was used to get out of the of Clifford quantum computing was this non-Gaussian state, for example, a cubic phase state or photon counting. What we did is we wrote another, if you will, recipe that only uses one non-Gaussian operation, that is just the GKP state itself. So the GKP becomes its own magic state that we can distill. How does that work? It's actually a fairly simple protocol because we just take the vacuum, we just do GKP error correction on the vacuum, or maybe I should call it GKP error projection, code space projection on this space, and we just look and we ask ourselves whether that state, the logical state associated with that, is distillable or not. And surprisingly, most of the states we get by just error correcting the vacuum are actually distillable. In this picture, we see the little white crosses are the states that are not distillable. So everything else is distillable with different fidelity, with respect to the Hadamard eigenstate. Oh, I should have mentioned, the Hadamard eigenstate in this picture is what we use to get to universality. And we can also be interested in higher fidelity with the Hadamard eigenstate, for example, and this is what we get if we also consider thermal states with different thermal occupation number. Now, this graph is not the easiest to read, but what it's telling us is that if we want a state with minimum fidelity on the X with respect to the Hadamard eigenstate, then our error correction on the vacuum protocol is gonna give us a magic state with success probability of whatever we have on the Y. So as we can see, when we consider thermal states, the success probability goes down by quite a bit. So I guess the vacuum performs much better. So yeah, I'd like just to sum up the key results, which are that now we have a tensor, we have a subsystem decomposition of a CV mode into a logical mode where we can perform, say, qubit quantum computing over. We can trace out, we can take any wave function that doesn't necessarily explicitly encode a state, and just get a logical qubit out of that. For example, periodic wave functions work very well with the GKP state, with the GKP code. The gauge subsystem is something we technically don't care about, but we might actually use to perform gauge fixing and to optimize the CV codes, that kind of thing. We also know that any approximate code word, any approximate wave function, a physical wave function is going to give us mixedness with respect to this decomposition. So this is a very reasonable interpretation of what an approximate CV code word is. It's just a mixed qubit. That's what it translates to. If we want a perfect qubit, we need infinite energy, in the GKP case at least. We also see like this interplay between discrete and continuous variable cluster states, which is kind of cool. There's always been a hidden discrete variable cluster state inside these fully Gaussian CV cluster states, and we retrieve logical information by just GKP projecting with GKP measurements, and then we disentangled our DV discrete variable subsystem from the underlying gauge subsystem, and this is the other result: universal fault-tolerant continuous variable quantum computing with GKP error correction and the vacuum state alone, which is, yeah. And thank you very much for your attention.
So, are there any questions? Maybe let me start with one. So when you do this GKP projection, starting from the vacuum state, I mean, you will get different states all the time, right? I mean, is that a problem for distillation, or can you just fix it by some?
We can always trade off the difference in the states with classical information for more mixedness. So we can twirl our states back to it's a trace decreasing operation, but we can always mess them up a little bit to get something that's distillable and that's with some fidelity with respect to the atom or eigenstate, for example.
Any other questions? Yes, maybe.
Hello. So when you give the fidelity for what the magic states are, is that with respect to this logical space, ignoring the gauge degrees of freedom? Yeah, and I guess the answer to that is yes. And then what I'm leading on to next is...
No. The answer is actually no. Well, it turns out to be equivalent because it was a much more cumbersome calculation because we didn't have the framework to actually trace out the gauge subsystem. So after working with that, it turned out to be much simpler because the tracing out operation was defined. But that was just with respect to overlaps of the Wigner functions for the ideal code words, which is
ideal with some amount of squeezing. So
I think infinite amount of squeezing.
Yeah.
The fidelity is computed as just the overlap, between. Yeah.
Okay.
I think so. I'll double check.
I think there was a question in back, maybe not.
So when you do this distillation or this projection, get these magic states, did you do that with perfect GKP states as your...
as ancillas?
As ancillas, yeah.
Yes.
And what if they're not perfect? What good GKP states do you need to make this work?
So we're doing that calculation with the not to correct that result, but with respect to something else. But yeah, they change with some amount that depends obviously on the squeezing of the GKP state. So I would expect those fidelity graph all to go down by something that depends on the amount of squeezing that we have in the oscillators.
Yeah, but I was wondering if there was like a limit of you need that much squeezing before you can, just like you saw, you need to have, when you use thermal state, there was like a threshold, right? Beyond which you could not do it, or you had zero probability of success.
Yeah,
I was wondering if there's a similar limit to the quality of your GKP states.
There's probably going to be something like that, but what we have there is a pretty much just a proposition for a protocol. It's not a, we're not addressing that issue.
Oh, thank you.
Okay, we still have time for one question. Let me ask, do you think this correspondence to finite dimensional cluster states, you can use this perhaps to design protocols that use the gauge system somehow?
What are you referring to, the subsystem decomposition?
No, I meant the cluster state. I mean, when you measure it, you sort of disentangle the gauge system, but maybe you can use this picture that you have.
It would be nice to use that picture, but that example is always on ideal cluster states. What the computation is well defined. We can just trace things out and get a mixed cluster state. It's just that it doesn't have that nice representation in terms of lines and stuff. It does have that, but it's not telling much. It's not very insightful. But we can always just take anything CV for a CV cluster state, trace the gauge mode out, and what we get is a mixed state, DV, discrete variable state, mixed qubit.
Okay, so let's thank Giacomo again for this beautiful talk.